Okay, so far we have concentrated on detecting arguments and on describing them, but in this section we'll start to evaluate them. Now, to evaluate something, we need to have a criterion of what is good or bad in that respect. So, for instance, if I'm going to evaluate someone's singing performance, I must have a notion of what constitutes good singing and what constitutes bad singing. So without such a criterion, my evaluation would be arbitrary. It is traditional in logic to distinguish two main kinds of standards for evaluating arguments. One type of standard is deductive, whereas the other kind of standard is non-deductive. And this last group is sometimes known as inductive standards or also non-demonstrative standards. But today we'll start with deductive standards. If you remember, we had already introduced the notion of a valid argument. A valid argument is one in which it is impossible, at the same time, for the premises to be true and the conclusion to be false. Well, this notion pertains to deductive arguments. And so a good deductive argument must, at the very least, be valid. So deductive arguments aim at validity, nothing less. For a deductive argument to be good, it must be the case that if the premises are true, then the conclusion must be true as well. So since deductive arguments aim at validity, the relationship between the premises and the conclusion must be a very tight one. In a valid deductive argument, the truth of the premises guarantees the truth of the conclusion. Non-deductive standards for evaluating arguments are less strict, however. For instance, for an inductive argument to be strong, what we require is, for instance, that the premises make the conclusion likely or reasonable, or at least that it be more reasonable than its negation. And we can see that this is less strict than requiring that the premises guarantee the validity of the conclusions. But we'll discuss non-deductive standards later. For now, let's stick to deductive ones. We'll start our survey of deductive standards with the study of propositional logic, also known as sentential logic, which provides us a set of formal tools for evaluating validity. We mentioned the expression formal tools, but what does that mean? Well, what it means is basically using special symbols instead of words or sentences. For instance, where each of those symbols are perfectly defined and its properties are completely known. Now, why would we want to work in this new language? Well, here's an example. Imagine that you were told to evaluate this expression. A number multiplied by its successor divided by 2 is equal to the square of the first number plus the same number divided by 2. Well, notice that first you have to parse and interpret the sentence, which is somewhat cumbersome. Second, what is a successor? Third, now to keep track of the numbers involved, you have to keep referring to them as the first number or the second number, etc. Fourth, notice that the expression is ambiguous. Right? And fifth, that the English formulation, well, doesn't make it clear how to determine whether the sentence is true or not. When I say that it is expression, I mean this. So one way of reading it is to say that a number multiplied by its successor, right, and that's one expression, divided by 2 is equal to the square of the first number plus the same number divided by 2. And so what is divided by 2 is a number multiplied by its successor. So on another reading, we have that a number multiplied by its successor divided by 2 is equal blah, blah, blah. So now the things that have to be multiplied are on one side a number, and then the successor of the first number divided by 2. Now this is quite different from the other reading. But it's hard just to know from the English version. So now compare with this algebraic, that is formal, way of putting it. So instead of talking of numbers, we use n as a variable. And instead of talking of the first or second numbers, we simply repeat n as many times as necessary. Also, note that the expression is entirely unambiguous. Right? Third, the notation itself suggests how to manipulate the symbols. so as to convert one expression to the other. That is, if you know the relevant rules. Well, we won't be doing any algebra here, right? We won't be dealing with any numbers, at least in this first part. But the language of propositional logic is analog in some respects to algebra, in that it has the same advantages over natural language. It's just that instead of working with numbers, we will be working with sentences. Okay, now on to propositional logic. Our three objectives in this brief introduction to propositional logic are: first, to introduce a formal notion of validity; second, to learn to symbolize English sentences in propositional logic, which we abbreviate as PL; and third, to learn to test validity of arguments in PL. To do that, we will first have to get some familiarity with the logical connectives and with the devices called truth tables, as well as with the notion of propositional form. Let us begin with the notion of a connective. Sentences 1 and 2, Al swims, Beth smokes, are what we call simple sentences or atomic sentences, in the sense that they are not composed of other sentences. That is, they do not contain any devices like and, or, because, etc. Now, expressions such as and, or, not, if, then, are English connectives. And what characterizes them is their function, which is to take sentences and make more complex sentences out of them. Here are examples of complex sentences, which are made by combining the simple sentences 1 and 2 in various ways by means of the connectives. So we have not only Al swims and Beth smokes, but then we have Beth doesn't smoke, which is simply negation applied to 2. Or Al swims and Beth smokes, which is made by taking 1 and 2 and sticking and in between them. And then instead of and, we could have written or. Al swims or Beth smokes, etc. So if Al swims, then Beth smokes. It is not the case that Al swims and Beth smokes, and either Al swims or Beth doesn't smoke. Now, this is crucial. The key to how propositional logic works is the following, namely that the truth or falsity of a complex sentence depends exclusively on two things. First, the truth or falsity of the component sentences, right? This is what is called the truth value, whether they are true or false. And second, the way in which the component sentences are joined, that is, which connective we're using. So this means that for any complex sentence, if we know the truth values of its component sentences, and if we know the way in which the connectives are involved work, then we'll know whether the complex sentence is true or false. And notice that I say any sentence, because this applies to all sentences, no matter how long, even if it's 100 words long, or 1,000 words long, or 1,000,000 words long. Moreover, propositional logic deals with the validity of arguments when such validity depends on certain connectives, right? Such as not, and, or, and if then. Because these are the words that signal certain relations among sentences, and depending in how they are related, you may have an invalid or a valid argument. And propositional logic helps you to determine what is the case. These connectives that are studied by propositional logic also have standard names, right? You have the conjunction, which in English corresponds to and, but, etc. You have disjunction, which corresponds to or, negation, which corresponds to not or it's not the case. We have the conditional, which corresponds to more or less to if, then, whenever, and then the biconditional if and only if. For this part, we're going to concentrate on the first three.